Hi and welcome to my presentation. My name is Paran Pourteimouri and I'm a second-year PhD student at University of Twente in Water Engineering and Management Group. The title of my project is The Impact of Buildings Characteristics on Airflow Patterns and Bed Morphology at Beaches using CFD Modeling. My presentation is divided into 4 parts. I'll start with an introduction, including the importance of this study and the research questions. In theory, I'm going to talk about wind flow patterns around an isolated building. Next, I'll focus on the methodology that I used and some details of the numerical model. Finally, I'll present results and discussions on how buildings' characteristics influence the airflow patterns and bed morphology. Let's begin with introduction. The question is, what are the human interventions at beach-dune interface? To answer this question, let me show you the morphological loop and the interactions between separate components. You know that coastal zones are always attractive for humans. This highly increasing human population in coastal zones increases the demands for constructing restaurants, beach houses, and pavilions at the beach-dune interface. Buildings at the beach-dune interface create obstacles for wind flow, and as you can see in this figure, they change the local airflow patterns around the structures. These perturbed airflow patterns alter sediment transport pathways and bed morphology around the structures. In a longer time scale, it causes the reformation or the migration of an existing sand dune. If you look at the morphological loop, we started from the buildings at the beach and their impacts on airflow patterns, sediment transport, and bed morphology. But finally, the loop ends with the impacts of bed morphology on buildings. Why? The reason is that sand encroachment into houses disturbs the human activities, damages the properties, and causes economic losses. We will answer 2 main research questions in this study. The first research question is, what are the impacts of buildings' length, width, and height on airflow patterns? And the second one is, how can we predict the bed morphology from airflow patterns? Maybe you're thinking that how and to what extent the airflow can be affected by building. To make it clear, this slide shows the theoretical airflow patterns around an isolated cubic building. The top left corner shows the wind-facing side and the bottom right corner shows the lee side view. If you look at the flow field, you can see the complex recirculation zones in front of the building, on top, around the lateral sides, and also behind the structure in the downstream cavity region. The length and size of these recirculation zones depend on the building dimension, geometry, orientation, and so on. These locally perturbed wind flows alter the sediment transport pathways. The question is, how can we reach these goals? We developed a CFD model using OpenFOAM, which is an open source CFD solver, to simulate wind flow around an isolated building. And among all OpenFOAM solvers, we use SimpleFOAM, which is recommended for a steady-state simulation of incompressible and turbulent flows. SimpleFOAM solver uses finite volume method and Reynolds average Navier-Stokes equations. The governing equations are continuity and momentum equations as written here. In the momentum equation, nu EFF is the effective kinematic viscosity defined as the sum of the kinematic viscosity of the flow, nu, and the turbulent or eddy kinematic viscosity, or nu T. This turbulent kinematic viscosity is calculated by the turbulence kinetic energy K and its rate of dissipation epsilon, which is suggested by Richards and Hoxie. In this equation, C mu is a dimensionless constant and K and epsilon are computed from their transport equations using a standard K-epsilon turbulence closure model. Next slide shows the computational domain. A three-dimensional rectangular domain is considered for modeling airflow patterns around an isolated building which is located inside the domain. Considering the neutral stratification conditions, fully developed profiles of mean wind speed and turbulence quantities, including turbulence kinetic energy and turbulence dissipation rate, are applied at the inlet of the domain here. In these equations, K is the von Karman constant and Y0 is the aerodynamic roughness length. U star is the friction velocity and is calculated using this equation, where Uref is the reference velocity at a reference height Zref. Values of the atmospheric boundary layer parameters are given in Table 1, and Table 2 shows the definition and values of the geometric parameters of the computational domain and the surface-mounted building. The values are selected based on the wind tunnel experiments that are used later for the validation of the numerical model. Okay, next slide shows the results of model validation. Model predictions of the vertical wind velocity profiles at different sections in the vicinity of the building are compared with wind tunnel measurements performed by Lytle and Schatzman at Hamburg University. The results are given for the symmetry plane and at 6 different sections as mentioned above each figure. The comparisons show good agreements between numerical results and experimental measurements. Results and discussions are presented for 3 buildings' characteristics, including length, width, and height. First results show the impacts of building lengths on airflow patterns. The figures are top views and show the wind velocity magnitudes at the near surface horizontal plane at an elevation of 0.0125 meter. The building length is systematically changing from L double prime in the reference case to 1.5 times L double prime, 2 times L double prime, up to 3 times L double prime. However, the width and height of the building is constant in these 5 figures. The results show that the longer building makes no significant change on the length of the upwind recirculation zone in front of the building, which is defined as LU, or the length between the start point of recirculation region and the front face of the building. However, the longer building creates shorter downwind recirculation region behind the building, which is defined as LD, or the distance between the reattachment point and the rear face of the building. In addition, the longer building shows no significant impact on the overall length downstream that is influenced by the presence of the building. Next slide shows the impacts of building widths on airflow patterns. The results of wind velocity magnitudes are given at a near surface plane when building width is increasing systematically from W double prime in the reference case to 3 times W double prime. It is clear from figures that a wider building creates a longer and wider upwind recirculation zone in front of the building, and also the length and width of the downwind recirculation zone behind the building increases with increasing building widths. Furthermore, the wider building impacts the velocity magnitudes for a longer distance downstream the building. The impacts of building height on airflow patterns are shown here, And same as previous results, the building height is increasing systematically from h double prime in the reference case to 3 times h double prime. The results of near-surface wind velocity magnitudes show that the upwind recirculation zone in front of the building and the downwind recirculation zone just behind the building both increase in length with increasing building height. Furthermore, the velocity deficits continue for a longer distance downstream for a higher building. The question is, how can we predict bed morphology from airflow patterns? For this reason, we calculated the horizontal divergence of the velocity field for one case and then compared the results with field measurements of erosion and deposition patterns around scaled buildings at the beach like this. When the values of the horizontal divergence of the velocity field are positive, it can be concluded that the rate of change of flow is outward and it is expected to see erosion in that point. On the other hand, the negative values of the horizontal divergence of the velocity field show that the rate of change of flow is inward and the sedimentation is more probable to happen in that point. Looking at numerical predictions up in the building and close to the building front face, the values of the horizontal divergence are positive, therefore it is expected that the erosion happens in those areas. Looking at field measurements, you see that the erosion happens up in the building and close to its front face. The highest values of the horizontal divergence occur around the upwind edges of the building. Therefore, it is expected that extensive erosion happens around the upwind edges of the building. There is a horseshoe-shaped area in front of the building with negative values of horizontal divergence here, where it is expected to see sedimentation in those areas, and this is exactly what happens in the field here. Downwind the building and between the two tails of the horseshoe-shaped area, here, the positive values of the horizontal divergence increases the possibilities for occurring erosion in those areas, and again, this is the same pattern as in the field. Let's have a look at conclusions. Conclusion 1. The near-surface airflow patterns around the building are least dependent on the length of the building. Conclusion 2. The near-surface airflow patterns around the building depend most on the width of the building. Third one, the height of the building is also important for the near-surface airflow patterns around the building. And the last one, the results of horizontal divergence of the velocity field are comparable with the rate of erosion and sedimentation patterns. Thanks for your attention.